This is the Colorado School of Mines PIC Math team. I'm Paul.
I'm Chelsea.
I'm Kelsey.
And I'm Eric.
So we're going to flip to a slideshow and do a voiceover recording of our presentation for you guys. Hope you enjoy.
We're going to start by giving you some background information on both Ebola and our model. So, as many of you know, the current Ebola outbreak in West Africa is the worst in the history of the disease. The first case appeared in Guinea in December 2013, and as of April 2015, there have been more than 25,000 cases with over 14,000 confirmed deaths. This graphic is taken from the World Health Organization and shows the density of the outbreak in different locations with darker colors meaning more infections. As you can see, Guinea, Sierra Leone, and Liberia have been at the forefront of the outbreak. So the goal of our project is to determine the optimal location and place a treatment center to mitigate the spread of Ebola in West Africa for different potential outcomes. The metrics we use to determine best treatment location will be discussed later on in the presentation. So for our project, we have modified an SEIR model to account for many of the characteristics of Ebola. First, we have created a removed and infectious population to account for the spread of the disease that occurs when susceptibles come into contact with dead bodies. Second, we assume that people who have recovered from the disease are no longer susceptible, as antibodies in survivors last for at least 10 years. Third, we assume that hospitals have unlimited space. However, we do have a parameter which regulates how quickly people get into hospitals. Here's a state diagram to give some intuition into how populations move within our model. S represents susceptibles and is the general populations of Sierra Leone, Liberia, and Guinea. E represents exposed, which means a person has contracted the disease and is in the initial incubation period, which ranges from 2 to 21 days. At this time, they are not showing symptoms. From exposed, people become infected. Once infected, people are either lucky and move to hospitals, our H population, or they become removed and infectious, which is our RI population. However, once hospitalized, we assume the dead move immediately to removed and buried. Furthermore, both the I and H compartments can become removed and recovered. So here's our system of 7 differential equations with 11 parameters, 5 of which we had to fit, which is what we're going to talk about next.
Hi, this is Paul, and I'm going to talk to you about how we did our parameter fitting. So this was important because some of our parameters in our model, we just had no idea what they would be, and there was not really a good way to get data or literature values for them. So to do this, we were using the best possible data source we found, which came from World Health Organization reports, and this was country time series data of infected cases, case counts, and death counts. So to do this, we based our method on work done using SIR and fitting data to an SIR model. All of our simulations were done in MATLAB, and we were using the fmin search optimization function to do this. So that is, it finds the minimum of an unconstrained multivariable function using a derivative-free method. This works by minimizing an error iteratively. For our error function, we defined it based on the sum of squares. So we're trying to minimize the error between our model's infected cases and the data we have, and our model's death count to the data we have for that as well. Here you can see that our total cumulative death is the sum of our removed infectious and our removed buried populations, whereas the total sum of our infections is our I population plus the hospitalized population. So I'm going to show you one of the graphs here. This was for our best possible data set. In Guinea, we had 90 data points, and they were all very clean with few gaps in data. So what you want to see here is black lines corresponding to black dots. The lines represent our simulation, our model, our system of ODEs, and the dots represent our data points. I included this in here, this slide, to show you how problematic some of this data was. And it was most problematic in Liberia. You can see that there's really not much variation in the first 90 days, and at about day 200, there's a huge gap in infections, from 2,000 to 4,000. And this was due to 6 days in our data set for which there were just no data points. This was a pretty big hurdle for this parameter fitting method because it's very sensitive to initial conditions, and we just don't think that this data here is super accurate. So to make it fit, we had to truncate the data. This is the result. We started about day 80 and go up to day 200. But again, you can see that we got a nice minimization of that error. The lines and the dots line up pretty much exactly the way that we want to see them. Finally, this is our Sierra Leone parameter fit. Again, you can see that the error is being minimized appropriately here. Also to note, we had to truncate this data series as well. So with these parameter values, we were able to then couple the system. So now we have parameter values for each different country, and Eric's going to talk about how we did that.
Thanks. So, most epidemics are not localized in one country, and so we're trying to capture that idea by adding coupling between countries. So now you'll notice we have these 7 same differential equations that we had before, but now each population has a subscript I. What this means is that I can take the values of 1, 2, and 3, so now rather than 7 differential equations, we have 21. We have 3 sets of 7, and we modify it by adding a coupling term. The coupling term is this phi ij term highlighted in red, and this allows that exposed people from one country to be transferred into a different country. We assumed that infected would not be able to transition in this way because once you're infectious, you're symptomatic, and you'd be stopped at the borders. Using this modeling, or using this coupling, we were able to fit the parameters for phi just as we did before, as described by Paul. And so once we fitted the parameters, we have these new plots that show the correspondence between the model data points and our model. So here we see Guinea, Liberia, and Sierra Leone with the coupled model. And so just from looking at it with our eye, it's like kind of difficult to determine which fit is better. But we can look at the error function described by Paul, and we see that the error without coupling gives a value of 142, but once we add coupling, we get an error of 14. This says that our coupling is well-founded, and it makes our model fit the data better. For these initial conditions, we needed to kind of stitch them together because we were starting at different times, but we did this with MATLAB, and everything worked out to minimize our error. So now that we have our coupled model, we're able to start to make some claims about where we should place the hospital, which is what Kelsey's going to talk about next.
So we used a few different metrics to try to determine the optimal placement for a hospital in one of these 3 countries. The first metric we used was based on parameter values. We looked at our parameter values in each of the 3 countries to determine which one might have the most need for a new hospital. The first parameter we looked at was the hospitalization rate. This corresponds to 1 over the average number of days it takes for an individual to move from the infectious to the hospitalized populations. Here we see in Liberia this value is about 1/2, which corresponds to it taking about 2 days for somebody in Liberia to move from the infectious to hospitalized populations. In contrast, in Sierra Leone, this value is over 2, meaning that it takes less than half a day. This might indicate that Liberia has the greatest need for a hospital. Next, we looked at the death rate parameters for non-hospitalized and hospitalized individuals, respectively. We see here in Liberia this value is the greatest, which corresponds to the death rate being highest in Liberia. The death rate in Liberia is over 70% compared to the other countries, which are ranging from 40 to 60%. This indicates that Liberia might have the most need for a hospital. Next, we looked at the optimal placement of a hospital based on sensitivity analysis. We looked at the relative change in the infectious population steady state given a change in our parameter psi, our hospitalization rate. We see here that this value is large for Guinea and Liberia. This indicates that the infectious steady state would change dramatically given a small change in the hospitalization rate. This is what we want to see, meaning that a hospital would be effective in reducing the infectious population in either of these countries. Finally, we looked at optimal hospital placement based on minimizing the infectious population at the end of our simulations, which, reminder, it goes till December of 2014. To do this, we varied our hospitalization parameter from the fitted value to twice that value. Twice that value would correspond to it taking half as long for an individual to move to a hospital. We see here the effect is most drastic in Liberia and Sierra Leone, with it being the most drastic in Liberia. A 10% increase in psi corresponds to a nearly 50% decrease in the infections population in Liberia. With all of these metrics, we have concluded that, as of December 2014, Liberia is the optimal place to put a hospital. Next, Eric is going to talk about some of the future work we'd like to do with this model.
Thank you. So with this model, we've been able to take an SCIR standard model and adapt it based on the assumptions that we need by Ebola. However, we feel like we've just scratched the surface. We'd like to increase the resolution. Right now, all we can say is that Liberia is the optimal place to place a hospital, but it'd be nice if we could talk about the specific provinces of Liberia, which would have the most impact. Next, we've so far assumed that hospitals have an infinite capacity to take in patients, and we've only used this hospitalization rate as the means of whether or not there's a hospital there. But we think that if we were to introduce some logistic term which had a carrying capacity, then adding a new hospital would simply correspond to an increase in the carrying capacity, which seems like an intuitive method to look at hospital placement. We'd also like to try putting some patient zero in some country, and then allow the coupling terms to allow the Ebola to spread throughout the countries and see if that matches the data that we have. Lastly, in December last year, which is at the end of our model's validity based on our data, we found that China had in fact placed a hospital in Liberia, which agrees with what we said. It apparently has worked since, as of 2 days ago, April 28th, we found that Liberia hasn't had a new infection in 34 days. And so this lends credence to our model and gives us support that we came to the correct conclusion in saying that we should place a hospital in Liberia. With that, we accept any questions by email, and thank you for your time.